go longer and longer distances. So the electrical resistance would slowly drop towards zero. But the other argument was that at some temperature, the conduction electrons would recondense on the ions from which they would come, in which case the system would become completely neutral and the electrical resistance would jump to infinity. So Camerlionis obtained a very pure sample of mercury and gave it to his graduate student, Gilles Holst. I put the name up here because poor Gilles did not get his name on the paper that Camerlionis published. That was not his habit back in those days. I'm very happy that that habit was not the habit of my thesis advisor. Anyway, so here are the data shown here as these green dots, and you can see that this is temperature in Kelvin, so this is 4.2 Kelvin, the temperature where liquid helium boils at atmospheric pressure. And this is the electrical resistance in ohms, so this is only 0.002 of an ohm all the way at the top here. And so you can see, in fact, that as he's cooling, in fact, the electrical resistance is slowly dropping towards zero. But then, and quite unexpectedly, there was essentially a discontinuous drop in the electrical resistance to a value of less than 10 to the minus 5 ohms, which was the resolution of their instrument. So it took actually Gilles Holst quite a while to convince his mentor that a lead hadn't simply fallen off of the apparatus. But in fact, this was the first observation of superconductivity, which has been studied, I would say, every year in multiple countries around the world ever since that time. And so literally hundreds of times, Camerlionis, well, the thing I didn't tell you, if you wanted to study superconductivity for the next 15 years, you had to go to Leiden University, to Camerlionis' laboratory. He was the only one that could reach the temperatures where conventional metals would become superconductors. So literally hundreds of times, he cooled his liquid helium sample through the temperature of 2.17 Kelvin. That is the temperature where liquid helium becomes a superfluid. And in fact, at one point, Camerlionis wrote in his notebook that it appeared that when he pumped on the vapor above the liquid stopped boiling when the temperature got down to 2 Kelvin. Now, he never pursued why that was the case, and therefore he missed discovering that helium, liquid helium-4, becomes a superfluid at that temperature. So let's look at the research strategies that allowed these discoveries to be made and to not be made. First of all, use the best instrumentation available. In this case, in fact, by developing the machinery necessary to produce liquid helium, he opened up a world at very low temperatures, and of course he discovered new behavior. Don't reinvent, borrow technologies you can. Dewar had invented the double-walled, vacuum-jacketed Dewar called the Dewar, we call it a Dewar anyway. It's named after him, but the flask, Dewar flask, to hold his liquid hydrogen, and Camerlionis was very happy to use that technology in his own development of refrigeration processes. And then because of what he did, you can see that he actually looked at an unexplored region of the physical landscape. That is, that no one had looked at the properties, the behavior of matter at these very low temperatures. And then failure might be an invitation to try something new. Now, when Dewar had failed to liquefy helium before Camerlionis, he basically wrote a little note to Camerlionis saying, "Dear Camerlionis, you win, I lose Dewar," and Dewar basically got out of the business of low temperature, what we now call low temperature physics. But in this particular case, what I'm referring to is the fact that Camerlionis was unable to find where helium solidified, and so rather than giving up, he in fact looked at another very interesting problem and almost immediately made a major discovery. Now, I must say that people really didn't understand what superconductivity was all about in 1913, just 2 years later when Camerlionis was awarded the Nobel Prize. But in fact, that was the topic of his Nobel lecture. And finally, of course, be aware of subtle, unexplained behavior don't dismiss it. That subtle behavior may in fact be the signature of some important phase transition. So no one really got a Nobel Prize for having discovered superfluidity in helium-4. As time went on, people realized that there was a phase transition of some sort at this temperature of 2.17 Kelvin, but it wasn't really very clear what the nature of the ordered state was. And it was this gentleman, Peter Kapitsa, in the bitter winter of 1937 in Moscow, that was able to show that the viscosity of liquid helium below this temperature was less than 1/1000th of a poise, essentially zero viscosity, showing in fact that this really was a superfluid transition that had been discovered. And in fact, for that work, Peter Kapitsa shared the Nobel Prize in 1978. Now you can see in fact it was 43 years between the time that the work was done and the time that the prize was given. The average amount of time in physics is supposed to be 17 years. I don't know why it took so long in this case. But this was a very interesting Nobel Prize because, in fact, Kapitsa shared the Nobel Prize with two people whose work had absolutely nothing to do with his own. Those people being Arno Penzias on the left and Robert Wilson on the right, who were at AT&T Bell Laboratories. In fact, for many years, Arno Penzias was my boss's boss's boss at Bell Laboratories. He was the vice president of research at Bell Laboratories, and I was just a department head of the low temperature research department. So Penzias and Wilson, I think most of you know, had discovered cosmic microwave background radiation. And let me talk about that discovery just a little bit. So AT&T had been using this microwave receiver to do early experiments on satellite telecommunications. The first experiment was with the ECHO satellite project. I don't know how many people in this audience are old enough to remember that, but it didn't inflate properly. The idea was to reflect radio waves off of a mylar balloon that was filled with some gas, and it didn't fill up completely, so the shape was not spherical. Anyway, the next one was Telstar, which was a very serious satellite telecommunications experiment. And when that was over, AT&T gave this apparatus to Penzias and Wilson for their use in studying microwaves coming from outer space, basically radio astrophysics. Now, you might wonder why it was that a telecommunications company would be interested in supporting research in radio signals coming from distant galaxies and things like that. And it probably had to do with this person here, who's rather hard to see. This is Karl Jansky. Karl Jansky was working with directional antennas in 1933 when he pointed this antenna toward the center of the Milky Way galaxy. Now, you can't actually see the center of the Milky Way galaxy in the visible. You can see it in the infrared. In fact, my eyes were the third set of human eyes to see that. I was up top of Mount Wilson when that discovery was made, but I didn't make it. Anyway, so he pointed it, and what he found was there was a lot of radio noise coming from the center of the Milky Way galaxy. And so Karl Jansky is literally the father of radio astrophysics, and I would guess that he probably would have won a Nobel Prize, but he died at age 45. So one of the strategies for getting a Nobel Prize has to be you have to live long enough. So if you go back and look at this apparatus here, this is a horn antenna, which has the advantage that it doesn't couple any radio signals coming from the Earth into the receiver. But the receiver is actually in this shed here, and the most important part of